Hello everybody, this is Dr. Mohammed Haque. I will be your professor in Chemistry 1 in this semester. So today will be Chapter 1, Chemistry and Measurement. Did you guys finish your pre-assessment?
Yes, sir.
Wonderful. I will be giving you the initial when you have a break time. Okay? First of all, this is the contents that we'll be focusing Chapter 1. We'll be going over the first, one of the first laws in the universe is law of conservation of mass. And then the matter, what is matter, how you classify, how you change it, and then we'll be going over how you measure it, how do the measurement go with these matters. And then we'll be finishing up the chapter with the density and temperature scale. So first of all, one of the important theory is called law of conservation of mass. This theory is established by Antonio Lavoisier. He discovered that any chemical reaction, initial mass and final mass is going to be constant. So, for instance, if I have a chemical reaction, so I have a H2 plus O2 that makes water. So in this molecule, I am reacting hydrogen and oxygen and forming water. So the total mass of my reactant and total mass of the product is calculated as equal. So that means mass did not produced or did not created or destroyed. Whatever I have, that just rearranged. And this theory is very important because the atomic definition that we know of today, that actually established based on this idea. Because initially people thought that atom could be or matter could be divisible until infinite. So in a chemical reaction have two sides. One is the ingredient, one is the outcome. The ingredient side is called the reactant, and then outcome is called the product. So this is called reactant as the ingredient, and this is called product. So let me go a little bit deeper. If you see this molecule 2H2, look at that, 2 as a prefix, 2 as a subscript. What does it mean? Any idea? This 2 means, prefix means 2 molecule, exactly. And then subscript means 2 atoms, exactly. So prefix means the molecule and subscript means atom. So it shows that means I have 2 atoms and 2 molecules. The total, since I have 2 molecules, actually I have total 2 times 2. Actually I have 4 atoms. If I see the mass of this molecule, I have 2 times 1.008. So it about 4.03. So that means 4 gram of about 4 gram of hydrogen, and which has 4 atoms reacting with 2 oxygen atoms. And how much oxygen? I have 32 gram of. So I have 2 atoms, 4 atoms. So 4 atoms plus 2 atoms, 4 hydrogen and 2 oxygen, and 4 gram of hydrogen and 32 gram of oxygen. You see, and then it's reacting reacting. How many, let me ask you a question. How many hydrogen atom is producing in here? 4 atom, right? 4 atom of hydrogen. And how many atom of oxygen? 2. That means the total number was 4 plus 2, 6 atoms of molecule, or you can say 4 atoms of hydrogen reacted with the 2 atoms of oxygen. You see exactly 4 atoms of hydrogen and 2 atoms of oxygen produced. And you see in here, H and O, completely 2 different atoms in chemical character, in properties, and which produced completely new product, which is water. Is completely neutral water molecule, and there is no similarity, there is no similar properties between this reactant and product. That's called chemical reaction, forming something completely new composition, and their properties also new. So, and in this chemical reaction, what happened? Number of reactant is equal to number of product. Let's see the mass, what we are in right now. So the mass of reactant is total is 36 gram, right? What about the mass of product? Also 36 gram, which shows that the total calculated mass of reactant is equal to total calculated mass of product. That's proof that law of conservation mass, which Lavoisier established, it proves in every sort of chemical reaction. So this is a summary of the theory. So mass could be converted to one format to another format, but it's going to be equal. At the same time, atom is rearranging, but number of atom is going to be same in reactant and product. So you have a few more examples for you, how they're forming product from reactant. And there is another reaction. You see, the total mass of reactant is equal to total mass. Total mass of reactant is 158.72 gram, and product also 158.72 gram. So you can take a look this example for you. Any question?
No.
Wonderful, wonderful. And then go to the matter. Let me ask you, what is matter? Everything around us is matter. For example,
The chairs.
chairs, you and us, all of us, you and me, all of us. The building, right? Your paper, pen. So, backpack. So everything and everything you see around us, including you and me, are called matter, right? So that means whole planet is made of matter. So in chemistry definition, matter is, so in simple, all of you know that based on the state, it's 3 types. First is solid, is solid, and liquid, what we drink, the liquid, and the third one is gas. You see there, it's called gas, right? So solid, liquid, and gas. So solid is the one, if you see this picture in here, solid, you see it has specific shape and volume. It is incompressible. They're tightly held atom to each other. That's called solid. And for the liquid is the one which has a specific volume. You can say I have a 5 liter of water. This is 1 liter, I can see that this is 1 or 25 or 250 milliliter. So it has a specific volume, but it has the ability to flow, right? It occupies any space you provide. So that means it doesn't have a specific shape. But it has a chemical interaction to each other. It is staying together, as you see. but still it doesn't have a specific shape. You can change the shape because of ability of flow of motion. It flows, right? Excuse me. And the last thing is gas. What is gas?
Air.
Air. Does it have shape and volume?
No.
No, nothing. It is like always floating with a free motion and is bumping to each other constantly, flowing, constantly running. So and that's why it makes pressure, air pressure. So gas is the one doesn't have specific volume, doesn't have specific shape. For instance, in the room is full of air, right? You can compress whole room full of gas and compress that in a small container. What does it mean? What does it mean? It's able to compress. It doesn't have a specific volume, not even shape, exactly. So, you see how the gas is compressible. Look at this another example, how molecules are staying in 3 different states. So we always try to give water example easily. I wrote CC, the water example. The example I have in the screen, also water. So let me ask you, in which states, liquids, solid and gas, in which state atoms are in the closest distance possible? Liquid, solid or gas? Solid. And which state is the highest distance possible?
Yes.
Right? So that's how they move. And they have the solid, they have intermolecular attraction. But gas doesn't have it. That's why they are flowing around, making bumping to each other. This is so that was the classification of matter based on their state. So how many types of matter you can classify based on their composition? Initially, primarily 2, based on their composition. So earlier one was based on their state. This one was based on their compositions. Based on their composition, first look at if you have a matter. If you have a matter, what is it? Look at is it pure or does it have specific property? And if it has specific combination and property, that is called pure substance. And if not specific property, that's called mixture. If it doesn't have a specific property and combination, that's called mixture. 2 things, right? Property and combination. So give me example where they have a specific property and combination, and where it doesn't have a specific property or unique property and combination. Give me 2 examples from these 2 types.
Nitrogen.
Nitrogen is a specific property and combination or not? Or, so I said 2 property, 2 things. First 2 criteria is pure substance is the one which has specific combination and specific property, unique property. But the mixture do not have specific combination, not with specific property. So give me example of pure substance. Give me example of mixture.
So nitrogen will be, it has unique substance and unique properties. And
first is the nitrogen, right? It has unique property and unique combination. 2 nitrogen combined together, and its property is it gas. This is the property, and other properties of course there. And second types is if there is no specific combination, no specific property. Example is sand.
Okay, sand.
If you have a glass of sand with water mixture, do you think sand mixed with water homogeneously? It's not uniform throughout. It's not. So because sand will be storing in the bottom, and the glass is, even the glass is full. That means this is called mixture. This is called pure substance. Pure substance, right? And what is the difference between element and compound?
Element cannot be
elements cannot be broken down.
Exactly. Elements are smallest. Elements are made of smallest building block. If you look at the periodic table, in the periodic table you have all atoms, right? So element made of single types of atom, which is a building block of matter. For instance, so if element, that is, for instance, this is sodium atom. Sodium element made of single building block of sodium. It has, and if sodium and chlorine combine together, which is we call table salt, that's called sodium chloride. So this is the element, this is the compound. So elements are combined chemically, forms a compound. Even though it forms a compound, still it has unique combination and unique property. This is sodium chloride. It says salty. It's specific property. How it is combined? Two atoms combined together. You see, chemically combined. You cannot distinguish sodium and chlorine from sodium chloride. It is a one compound. Remember I said that two types of matter. Pure means, pure doesn't mean that only single type. It could be two types, but uniquely combined and same property. You cannot distinguish between two atoms. How about the mixture? All mixtures are same? Not necessarily. Some it could be uniform throughout. For instance, if you mix, if you sprinkle some salt or water, salt or sugar into the water, right? This salt or sugar uniformly mix throughout the water. That's called uniform. That is homogeneous solution. So, for instance, lemonade, right? So, for instance, lemonade, and brine. So, brine is called sodium chloride and water. The salt solution is called brine. So, brine, lemonade.
Oh, sorry.
Oh, I can't even read my writing. I said, what did you write? Okay, so lemonade and brine, they are uniformly mixed. How about the air? Homogeneous and heterogeneous? Okay, let me pause in here. I'll ask you in a bit. So, if uniformly mixed, that's called homogeneous, right? And if it's not, if not uniformly throughout, that's called heterogeneous. As you see in the screen, heterogeneous. Example is sand and water mixture. What other mixture? What other example you can give? What? Oil and water. Oil cannot, dissolve into the water. What else? Pizza, sandwich, pizza, right? We all love to eat, right? Okay. How about so let me write pizza, which you always like to hear. Me too. I'm not blaming you guys. True is true, right? Not necessarily true is always, beautiful. True sometimes bitter, but true is true. Healthy food doesn't mean that it's tasty. It could be bitter, still healthy. Most of the healthy foods are bitter. Example: green apple, celery, spinach. They don't taste good. But these are the most healthiest food in the world. The three food I said: spinach, celery,
Green apple.
green apple. These three, the most healthiest food even you can drink. What's that?
They're all green.
They're all green and leafy.
Like
Something you see leafy and bitter, that's the healthy part. But not the, something is poison, I don't mean that. Because poison sometimes also could be bitter. Green too. Remember I give you example? The fate of Socrates, right? He was given hemlock, pure green, 100% natural, and he died. Okay, so pizza, right? It's a heterogeneous. Now let me ask you two examples. Our blood and air. Is it homogeneous or heterogeneous? Okay. Okay. Let me break it down more. You take an air sample in this room, or you take air sample from the 45 highway. So Highway 45 air is more polluted than from this classroom. So tell me, is it always homogeneous? Not always homogeneous. Same thing, blood. It is homogeneous naturally, apparently, but not always. These two examples, I see a lot of confusion. Is a homo or hetero to the student society. So I break down that it could be hetero, it could be homo. But so the key point of homo and hetero difference is the magic word is dissolve or solution. Something it says dissolve, it is going to be homogeneous. You see, salt and they said if you sprinkle salt and sugar, it is going to be homogeneous because you're mixing with water, it uniform throughout. So anytime it says solution, anytime it says a dissolve, that is called homogeneous. So if you go each of them, for instance, what is element? Element is single building block, which is atom in the periodic table, like a hydrogen, carbon, oxygen, right? You cannot break it down anymore. If you look at the compound, compound is which made of two atoms chemically, and this is the concept check for you. Tell me, A is atom, molecule, compound, homogeneous mixture or heterogeneous mixture? First one is element. Wonderful. What did you say? He's right. She's right. It is atom because elements are made of single building block, which is atom. So, and the second one, compound, exactly, chemically combined. You see, they're uniform and they have same types, pure substance, pure compound. The last one, mixture. We don't know is hetero or homo because we don't see that. We don't know is solution, dissolve. Remember the keyword, solution and dissolve is the homogeneous. And in a summary, metals are two types. If pure, that's substance, non-pure, mixture. If pure is type of single building block, it is element, more than one single building block, that's the compound. And mixture is dissolve or solution, uniform throughout, that's called homo. If not, that will be heterogeneous. Now, we're going to be talking about very important changing of metals. So metal could be changed different state or different ways. If it is changing physical properties, that's called physical change, and other one is called chemical change. So physical change is composition of property. For instance, if you, the example I have in the screen, you have a liquid, when temperature rises, it becomes gas, water vapor, right? Yes. Think about it. If you have a liquid, and this is the liquid that you have. This is water, right? Water. When it's floating around, when it's evaporating, that's becoming water vapor. So let me ask you, when it becomes water vapor, what is the combination of, what's the compound is in the vapor state? So it is H2O in the liquid, right? When it evaporated, is it still H2O?
Yes.
Yes, it is. There is no chemical reaction or there is no chemical product involved. So still it is H2O, even though it is vapor. So liquid and vapor, in both states, there is no permanent composition change. The composition is same. That is called physical change. Where there is nothing permanent change or nothing composition change. That's called physical change. What is chemical change? Chemical change is the one where it's changing its composition and it's transforming to new kind of matter. This is called chemical composition. For instance, so what was happening in this reaction? The penny melted to, yes, melted to the acid, right, or some solvent. The penny melted, it was copper penny, and when copper melted to acid, it formed completely new compound. So penny made of copper is reacting with the nitric acid with forming copper nitrate. It was a penny, copper, just metal. Is there any metal existing here? It's completely new compound. This is called salt. It's called salt. Completely, it was a metal, now it is a salt. And this salt cannot reverse, it's not reversible. You cannot reverse that back to metal. That shows that this is chemical change involved. So 2 points you can remember. One is changing the composition and changing its property, and it's not reversible. That's called chemical change. Chemical change have some properties, some sign. For instance, it's changing its color. It's making a precipitation. So if it is forming a precipitate or changing a color, can you make these leaves go back to green?
No.
No. It's permanent change, right? It's not reversible. Also, it's forming gas. Sometimes when you sink limestone into the water, it forms carbon dioxide gas, bubble. So forming a bubble means that it is something chemical reaction going on, something permanent stuff is producing. So that's called chemical reaction. And the last thing is it changing its color, which is change property. So these 5 things are the sign of chemical reaction or chemical change. Then if I ask you what happening is a physical or a chemical change when you're cutting a paper? Physical change, right? And how about if you burn a paper? that chemical. Because ashes cannot go back to the paper. But when you cut it, when you squish it, smash it, you can get back to the paper again. That's it. Chemical change. Ice is melting. Physical. Wonderful. So you're toasting or burning? Chemical, right? Chemical. Physical. And rusting. Because it's completely new product is forming, rusting, metal react with oxygen. So new product is formed which cannot go back to the metal. Candle burning, sometimes you might see, hey, some candle comes back to the bottom. That's actually not burning, it's coming back. It's not burning, if burn is gone. Okay? So it is chemical. What is physical property? Physical property is kind of characteristics of physical change. It's kind of an adjective. So physical change is adjective of physical change. So for instance, the physical property are the property which is actually physical change. So since you understood that what is physical property, physical change, now you understand that this is just an adjective format of physical change. For instance, boiling point. If you boil something,